Welcome to Math 70. The video lecture is for section 2.2. This is more about tables and graphs. So let me remind you of the four representations of mathematical ideas. Numbers are often represented as tables, but they can also be coordinate points or ordered pairs, and so we're going to see that. And the visual can be pictures, but it's often, especially in algebra, it's often graphs. Each of these representations can be turned into a different representation, which can be helpful when we ask and answer questions about mathematical ideas. So to start with, I'm going to give you an orientation to what a mathematical graph looks like. So in 2 dimensions, which is, I promise, the biggest number of dimensions we're going to be working in this class. We draw our graph, and I know you've seen this in previous videos, but I'm going to go through it in detail now. We draw our graph as what are called a set of axes. Axes is a plural for the word axis. An axis just means line of reference. We have our horizontal axis. This is almost always going to be the input variable, and we frequently just call it the x-axis because we usually use x as our input variable. And we have the vertical axis, which is usually going to be our output, and we often call it the y because we usually use the y-axis. And so I'll be using those three interchangeably. I try to stick with x and y in my examples because I like the consistency. But you can imagine if your input is time, then this would be your time axis, and maybe you would use the letter T. Or if your output is dollars, like cost in dollars, you might call this the cost axis, or you might call it the C axis, C for cost. The place where the two axes cross is called the origin. That's where the x and the y are both equal to 0. So the 0, 0, or the origin. Any point along the horizontal axis we say is on the x-axis. So if I label my axes with some numbers, 1, 2, 3, 4, this point right here is where the x value is 4 and the y value is 0. And similarly, moving up, this point right here is where the x value is 0 and the y value is 5. So this would be on the vertical axis or the y-axis. The more I draw, the more cluttered it's going to get. So feel free to reverse the video to check again. Horizontal axis, vertical axis, place where they meet is called the origin. When we have these two axes, we end up with 4 parts of our coordinate plane, and each of these parts has a different name. This part is quadrant 1, using the Greek Roman letter 1. Using the Roman letter 1. In quadrant 1, x and y are both positive. Like this point right here, I don't want to use that point. This point right here is the x is 4, the y is 3, and those are both positive. The next quadrant, we go this way, is quadrant 2. Here the x is negative and the y is positive. So like this point right here is -3, 1. The x is -3, the y is +1. Quadrant 3, the x and y are both negative. So this point right here, the x is -3, the y is -5, and quadrant 4, sorry, I at 4 or IV, the x is positive, the y is negative. This point right here is +1 to -3. Like I said, it got really cluttered really fast. So if you want to review, the best thing to do is watch the video as it flows out and not just try to draw all your information from this one cluttered picture. So looking back at our representations, this section is about going between numbers or tables and pictures or graphs. So this relationship right here. So I'm going to give you a couple different examples of that. We've seen a numerical representation, x's and y's. So let me just add in a couple coordinate points. Let's see, what other ones do I have? 4, 3. Maybe I'll come back and add another one later. But if this is my numerical representation, and I want to plot it on axes, we usually put our x-axis as the horizontal and the y-axis as the vertical. Let's just start plotting the points. So x is 0 means x should be here, and y is 2. So the point 0, 2 is on the y-axis. -1, 4. X is -1, y is 4. This is in quadrant 2. 3, 0 means x is 3 and y is 0. This is on the x-axis. -5 and -1. Means we're in quadrant 3 and 4. 1, 2, 3, 4. 1, 2, 3. Right there. Means we're in quadrant 1. And let's do one more point. Let's do 2, -3. That's 1, 2, 1, 2, 3 right here. 2, x is 2 and y is -3, which puts us in quadrant 4. That's how you go from a numerical representation of a table to the associated points on a graph. These were just random points I picked to show you how you can have things on the y-axis in the different quadrants and on the x-axis. One of the advantages of a graphical representation is it can help you see the form of the expression or equation or functions. Graphical representations show form quickly. So let me give you an example. Let me pick some different values. I'm going to march up in a, I'm not going to go back down, right? But I'm also not going to go up by 1. Here, x is going from 0 to 2, and then it increases by 1, then it increases by 2, then it increases by 10. Let's see. And I've got some y values. Now, I created these, and I think I did it right, but I would not expect anyone just glancing at that to say, I know what form these coordinate points take. I know that they're in a line or in a curve or go back and forth. They just look like a bunch of points, a bunch of random points. But when we put them on a graph, I'm not going to be to scale here perfectly, but let's see. Let's make the sorry. Let's I'm going to make this 2, 4, 6, 8, and 10. And I'm going to make this 5, 10, 15, 20, 25, like that. So when x is 0, y is -5. When x is 2, y is 1. When x is 3, y is 4. When x is 5, y is 10. And when x is 10, y is 25. And all of a sudden, we see, other than my drawing's not great, we see that these points live on a line. So if I were to ask you, what's the shape of these points? It's hard to tell. But if you were to put them on a graph, and I were to ask you what's the shape of these points, you would say, oh, this is a linear relationship between x and y. And that's good information because that means we can use the linear tools that we've been developing. We don't have to do something brand new to understand this information. We get to use our same linear tools. Just to show you how it actually is linear, I'm going to switch over to Desmos and put those points in. As a table, I had 0, 2, 3, 5, and 10 for the x, and the y's were -5, 1, 4, 10, and 25. Notice my scale is really bad. If you click the home button, it resets to the basic scale. And you can zoom in and out with the plus or minus, or just your standard mouse or trackpad zooming. And double click will, because double click doesn't zoom it in. I thought maybe it did. But there we can see, yep, those do look like they lie pretty much on a straight line. And so this is a linear relationship. Now let's look at a different table, and we should be able to see pretty quickly that it is not a linear relationship. Let's just do a bunch of different x's. And now when we look at this data, or these coordinate points, we can see, yeah, there definitely is not a single line that all of these points follow. If I were to move from left to right, I would have to jump up and then up again, and then way down, and then way up, and then way down, and then way up, and way down. That is definitely not a linear relationship. Let's do another one. I'll use the same 8 input points. Uh, All right, now what I have here are a set of points that don't lie perfectly on a line, but if you were to squint and make your eyes a little fuzzy, it kind of looks like they lie on a line. So we would call this a relationship that is approximately linear or close to linear. And one of the really nice things about Desmos, and this is going to come up in later parts of the course, is in Desmos, you can put your coordinate points in, and then you can click this button right here, which says Add Regression, and it will draw you the line that best fits that data, and even give you the formula for that line. So these coordinate points do not lie perfectly on a line, But if I were to pick the best line, the closest line, this would be the symbolic representation of that line, and here's the graphical representation of that line. It's called the line of best fit, and it can help you see if it makes sense to think about your data as approximately linear. Okay, I'm going to hop back to the notepad and just write down these ideas so that you have them in your notes. This one is a linear relationship, so a nonlinear, like a very nonlinear relationship. I'm just going to show you graphically what that might look like in terms of coordinate points. It might look something like this, where you're going up, you're going down, you're going all the way around, but definitely if you were to connect those points, you would want to kind of move your pen in a curvy way instead of a straight line. And then a approximately linear relationship. This one is kind of an approximately linear relationship because I didn't draw it very well, but I'll draw one that's a different example. It might look something like this, where it's not just a single line that could connect all the points, but there is a line that these points kind of follow. And we call that the line of best fit. And it does have a formula that you can use to get close. And maybe not in mathematics, but in a lot of sciences, getting close is the best you're ever going to do. Okay. All right, so we so far have been going between numerical representations and graphical representations. This section also touches on going from numerical to symbolic. An example of that is decide if the point xy equals 5, -3 is on the line given by y equals, hold on, I'm going to pause the video so I can actually come up with the formula that I need. Y equals -2x plus 7. So we're given a point and we're asked, does this point show up on the graph of this equation? Now there's actually a great way to answer this is you could switch to a graphical representation and just grab Desmos and graph that line and then see if that point is on that line. That's good algebra. But if we don't have Desmos, we can also test it simply by putting in the x value and evaluate to see if you get -3. So we have -2 times 5 plus 7, which is -10 plus 7, which is -3. Yes, if we have x equals 5, we get y equals -3. So that point is on the line given by that equation. What about the point xy equals, I'm going to keep it easy for myself, 4, 2. Right, is the point 4, 2 on the line given by that equation? So let's just try it. -2 times 4 plus 7 equals -8 plus 7 equals -1. But -1 is not equal to 2. So this point x comma y is not on the line y equals -2x plus 7. And again, in Desmos, it would be really quick and easy to see that. Let me show you. Pull Desmos up. Close this. let's put in the formula, y equals minus 2x plus 7. All right, we said in the first one, when x is 3, oops. No, when x was 5, y was minus 3. And there it is, there's the 0.5 minus 3. And if x is 4, y is 2, so I can even put those points in. Actually, let me do it this way. 5 minus 3, sure enough, it's right there. And 4 comma 2, nope, definitely not there. I want to take a moment just to show you another way to write this same equation that makes it even easier. And we're going to get more into function notation later, and I'll explain it in greater depth. But if you've seen it before, you know you can write your output as the function applied to x, which we say f of x. So if I write it that way, oops, I get the exact same line. And now I can say, what output do I get when x is 5? Oh, I get an output of 3. What output do I get when x is 4? I get an output of -1. I misspoke on this one. What output do I get when x is 5? -3. What output do I get when x is 4? -1. So writing our linear equations actually as linear functions helps us do arithmetic even a little bit faster using Desmos. All right, that's it for this video. Next one's coming up soon.